So chemical kinetics. Chemical kinetics is about how fast a reaction goes. Okay, so kinetics implies like motion. So we are interested in how fast. So let's say you don't have a speedometer in your car. But I know you all do, unless you get pulled over by a police officer and you're like, well, I didn't know what it said. How do you know how fast you're going in a car if you don't have a speedometer? Measure the time and the distance, right? So we're going to do the how fast, like when you think about miles per hour, right? That's miles over hours like this. That's what we call a rate. How fast something is going. This is a rate. It's a quantity and a unit of time. So we're always going to have some sort of unit of time. In chemistry, what do you think our quantity is? There's a lot that we use, actually. It could be liters of gas. It could be... What's the M word? No. Moles or molarity. There's like a lot of M words. Mass, right? Any of those M words, those are all quantities. So when we want to know how fast something goes, right, we just say this is how much quantity over a unit of time. So that's the way we do that, okay? Okay, so we talked about science of a chemical reaction, and you guys kind of told me. And if you want to measure these chemical changes, you got to do things like measure the amount of light or measure the amount of heat, right? Like you saw, I think pretty clearly, like how much faster the reaction was when I just dumped it in, right? Into that big tube. And that went faster. And part of what we want to do is understand what changes and affects the rates of reactions, but part of that is being quantitative, being able to measure how fast a reaction goes, okay? And we're going to spend a lot of time talking about that. I kind of wanted to show this, but maybe I'll just do this in class. Let's see if this works. Nope, didn't work. Let me see if I can click on it over here. I actually have this set up to do it. Maybe it's not working. Yeah, maybe I'll just have to try to do it. Let's do it. I don't know if you're going to be able to see it in here. All right. Yeah, we'll try to do it. We'll see what happens. This is 0.3 molar hydrochloric acid. And I'm going to pour a little bit in here, and if I get it on the carpet, don't tell anyone. This is like so bad I shouldn't do it like this. But, 0.3 molar hydrochloric acid is not that bad. The other one I'm going to do is 6. This one's a little stronger. It's still considered dilute. Like when you're dealing with acids as a chemist, anything less than straight up concentration is considered dilute. So like for hydrochloric acid, the concentrated, what you can buy is about 37% or 12 molar. So 6 molar is considered dilute. I told them to get me gloves for this, but I decided I think I can do this without spilling it on myself. Okay. And then I have these little strips of magnesium. They weigh about the same. So I want to design an experiment. Right? Same mass of magnesium for each. I want to be able to tell which reacts faster. Right? What's the simple thing that you can do? You throw them in. The one that's gone first, that one's faster. Right? That makes sense? There's other ways you can do this, and I don't know if this is going to get messy or not, so I'm going to push it back over to here. And I think, let's see what I did with my goggles. Did they hide my goggles on me? Put them over here. Yeah, I always lose these. Always useful to have people tell me where my goggles are. All right, let's try this. So here's the 0.3. Thrilling. All right. Well, what does 0.3 molar mean? It's a concentration, and it's 0.3 moles per liter. Now this one's 6, right? And you can see it's reacting. And I don't know if you can see this. I'm not going to do that with this one because I don't have enough time. All that little whiteness in there, right? Those are gas bubbles. So if you wanted to be a little bit more accurate about this, if you want to actually measure the rate, what you end up doing is you just measure the amount of gas that comes out. You could measure the pressure, right? You can measure the volume of gas. There's all kinds of things you can do to tell what the rate of the chemical reaction is. Now this one's 6 molar, so let's make a prediction, faster or slower? Faster, okay? And we could actually time it. Originally I had like 3 concentrations. We're going to do stopwatches. But then I realized this one's going to take forever. This is 6. It's bubbling so fast it actually won't go to the bottom. And that's hydrochloric acid fumes. So probably don't want to smell it. And it's getting really hot, by the way. I'll stand back here in case it ignites. It's a good thing this is a big room. Yeah, so which one's faster? The higher concentration. Okay, so we're going to get into this question, though. That's one aspect is just being able to measure. So this one's done and this one's still going, right? And I actually have, if you guys want to look at it later in lab, I have a 1 molar here. Yeah, I have a 1 molar as well. And if you really wanted to, you could take a stopwatch and time how long it takes each one, and we could calculate a rate, right? Grams per, and then just divide by the time. A lot of times we do it in seconds, okay? But you could do it in minutes. Like, what makes more sense for this one is minutes, because it's still going, right? It's still reacting slowly. There's still bubbles. It'll probably be going a little bit even by the time I'm done lecturing. All right. So, molecules, 3 things have to be true, okay, for a reaction to take place. And these are the 3 things. The molecules have to collide. Like, think about a chemical reaction, right? You want to make something, and feel free to write notes even if I don't write. So I thought about this over the break. It's important for you to have notes, and it's important for you to write. But you don't have to write these things. I wrote them for you, right? But write like, oh, that's why that is, right? Write notes to yourself about what that means. Try to write. The more you write, the more you'll remember, okay? Okay, so we're going to look at the things that influence reaction rates. But in order to understand that, we have to understand what do you need to have happen for a reaction to take place. And then we're going to bring all the rates and the collisions and all, we're going to bring all that stuff together, okay? But molecules have to collide. So if I have 2 things that I want to make, so for example, let's say I have C6H12O6, like glucose, and I want to burn it, right? And then, so I'm going to have to add oxygen to it, so I add O2 to it. And then I get CO2, and I get water. I'd say, what kind of reaction is that? Combustion reaction, right? And then I have to balance it, so I'm going to put a 6 here and a 6 here, and then you end up having a 6 there, and then that ends up being balanced out. That's the balanced chemical reaction. And we don't think about this in Chem 1A, but in order for that reaction to take place, the oxygen has to collide, actually has to come in contact with the glucose. Okay? And then the other thing that you have to do is you end up having to break bonds. Like John Dalton, the atomic theory guy, his early concept of chemical reactions was it's the rearrangements of the bonds between atoms that happens during a chemical reaction. That's how you get new stuff. Okay? So you have to have enough energy to break a chemical bond. That's Like, think about when I heated it, right over here. I got hot. And then once it was heated and it was lit, the reaction just took off. It was that fire, that stream of fire that came out. Well, you have to have enough energy to break the bonds in order for that to happen. Turns out, okay, and we'll talk about this more later, turns out like that's a spontaneous reaction. Like if I just left the lycopodium powder in the presence of high concentrations of oxygen for a long, long, long time, eventually it would turn into carbon dioxide and water, all on its own. It's spontaneous. It might take 1,000,000 years, but it's going to be spontaneous. Same thing is true for you. Like what we're constantly battling is like our bodies, like, okay, I'm battling more than you are right now. But as you get older, right, like your skin gets like tougher and it starts to wrinkle, and it's depressing for you guys. But, so I'm there. It's okay. Yeah. What's that? From oxidation. That's an oxidation process. And in fact, that could happen. That's like you're basically oxidizing. Combustion is an oxidation reaction. Basically oxidizing slowly. Eventually, you're done, and then you get cremated or buried or whatever happens. Okay, but you have to have enough energy. So the enough energy is you have to have enough energy to break bonds. These have to collide with each other. And here's the other thing that people don't think about. When two molecules collide, if they don't collide the right way, you don't get the right product out. So orientation of the collision is important, okay? So if the molecules don't collide, with correct orientation, the wrong product comes out. Oops. Or you don't get anything at all. Okay. So this is my stupid analogy. Okay. I'm going to do a handshake. This is my stupid handshake analogy. Somebody I don't know, because I don't know you. Where are you? Daniel. Okay, stand up, Daniel. We're going to do a reaction. Nothing weird. Ready? Yeah. This is the reaction. The product is a handshake. Got it? Okay. Now, what if I don't have enough energy? Yeah. Not enough to turn this. Let's turn this way. Stand up here. Make you sit. The way this classroom is. Anybody know this guy? No. Okay. He's a nice guy. This. So ready? Okay. See, that's not enough energy on my part. If I don't come in with enough energy, we can't shake hands. There's no product that's formed from that. Okay. Let's do this. Ready? So this is the reaction. I'm one reactant. He's one reactant. We get a handshake. That's the product. Ready? We're gonna do this one. Ready? Let's do it again. Wrong hand, right? Wrong orientation. So this is why it's important. If molecules want to produce the right product, they have to collide with enough energy and the correct orientation. Okay.
What creates isomers?
Oh yeah, have a seat. Isomers, depending on the type of isomer, sometimes it's collisions in the wrong orientation. So we'll talk maybe at the end of the semester a little bit about stereoisomers. Stereoisomers are formed when the molecule collides from one side or collides from the other side. And you get the mirror image of the molecule.
So it's just because from the incorrect orientation.
Yeah. So let's say okay, so we're going to play this game. We're going to play a game with. We can do this. This is a right-handed handshake, right? That's one of the products. This is the other product. It's a left-handed handshake, right? Now, if both things are possible, you end up with two products. Let's say one of the big goals in chemistry, like in pharmaceuticals, is to get one product. Do you guys know the inhaler that people use for asthma? What's that drug that they use in there? Albuterol, right? Comes in a left-handed version and a right-handed version. Turns out one opens up your airways and the other one closes it down. So when they made albuterol initially, what they figured out was, they did hospital studies, right? They looked at all these people that came in, severe asthma attack, and they gave them albuterol. Turns out some people's airways would shut down when they got albuterol because they had the wrong, right, exactly the opposite of what you wanted, because they had both isomers present in the drug. And then eventually they figured out how to remove one of the isomers by controlling how it was made. It's like controlling the orientation of the reaction, so you only got one product. And that greatly reduced, like by 70%, the number of incidents that were like that. Right? So the orientation of the molecules is important when the two come together. Okay. I should have a copy of these open for myself so I kind of know where I'm going. By the way, I rewrote these. I've had these notes forever. And I decided I don't like them, so I rewrote them. Okay, so let's look at some of the factors that... oh, wait. There's an animation here somewhere. Yeah, Dexter. Why do these four things influence? These are the things that they say affect the rate of a chemical reaction, right? Reactant concentration. Why does that affect the rate of a reaction? The answer might be obvious, and you can say it. It's okay. Don't think it. If it's wrong, I'm just going to be like, well, no, that's not it.
It's like that reaction right there, the stronger one reacted quicker.
The stronger one reacted quicker, but why?
If the higher concentration is more likely to have more molecules collided with each other.
Yeah, it's the number of collisions that you can have. So if you double the concentration, guess what you do with the number of collisions? You double the number of collisions. The frequency of collisions that can produce a product doubles as you double the concentration. Okay? Now I'm going to tell you, there are reactions where you double the concentration and nothing happens. And that's telling us something too. Okay? It's telling us about what steps are important in the chemical reaction to make it go forward. So, yeah, reacting concentration, increases frequency. Of collisions. And then of those collisions, right, you'll double the number of collisions that have the proper orientation. So increasing concentrations can be a big factor. What does temperatures affect? Why does changing the temperature? How fast the molecules are moving. So temperature is related to kinetic energy in molecules. We say temperature is related to kinetic energy. That's the energy necessary for the chemical reactions to break bonds so that new bonds can be formed. Right? You've got to be able to break things apart in order to make new things out of them. So like I have a car and you're working on a car, right? And you need parts for it. If you're like me, I just go to the shop and somebody does it for me. But if you're like a lot of people I know, they go to the junkyard and they break apart old cars, right? And they make new cars out of them, right? Okay. So you have to be able to break things apart in order to make new things. And so reactant temperature, this is the energy necessary to break bonds, so that new things can be formed. Now, what we saw out here, one of the other aspects of making a reaction go faster is surface area. Why would surface area matter? Like if I take a sugar cube and put it in water and stir it, or I take powdered, like granular sugar, not powdered sugar because it has other problems, but granular sugar and put it in, which one dissolves faster? The regular sugar does, right? The cube doesn't, because its surface area isn't as high. Why is surface area important?
The touching of the reactants?
Yeah, the reactants have to touch. More surface area means more area where the reactants can touch. So really, surface area is the equivalent to concentration. If you double the surface area, you double the contact. Okay. Car catalysts, like catalytic converters. I don't know, you guys probably know this. They put platinum catalytic converters. That's why some cars that have more platinum in them, they get their catalytic converters stolen, and then they sell them for the platinum. Okay. Well, I probably shouldn't tell you that. Maybe you didn't know that. Now a bunch of my catalytic converter will be gone. But yeah, they sell them. But the platinum that's in there, what color is platinum? Does anybody know? It's a metal. Yeah, it looks like silver, actually. It's silvery colored. But if you make the particle small enough, it doesn't reflect light anymore. It's called platinum black. Okay? It's such a small particle of platinum that you can't actually see it. It doesn't reflect any light. It looks like black powder. Okay? The reason they do that is by making the particles smaller, you increase the surface area. So in a catalytic converter, rather than putting big chunks of platinum in there, because then everybody's cars would be stolen for platinum, right? They put this platinum black in there, suspended inside a matrix to increase the surface area so you don't have to put that much platinum in there, okay? Some of the catalytic converters don't all use platinum, but some of them use like nickel, I think. But yeah, primarily original catalytic converters had platinum on the inside. So yeah, surface area is important because it's the same, it's similar to concentration. Increase the amount of collisions. Now, there's a thing called the catalyst, and we're going to talk about catalysts at the very end. But what a catalyst does is it simply lowers the amount of energy needed for the reaction to take place. And the way it does that, right, is by holding the reactants. Usually how it does it is holds the reactants close together in the proper orientation so the reaction can take place. Okay? So like normally in solution, two things have to like collide, right? And with the right orientation and enough energy. Well, what a catalyst does, grabs one of them, waits for the other one to come around, grabs the other one, puts them together, and once the reaction takes place, it lets go of them. So it speeds up the reaction by taking the place of the orientation, and it helps lower the energy that way. Okay. All right, I'm going to skip some of that. Okay. So remember I said that we have to measure rates. And so we'll talk a little bit about what rates are. And you can measure a number of different things. Like the rate, you can measure molarity units, right? You can measure concentration. You can measure pressure. You can measure mass changes. When I say concentration, I'm talking molarity, right? Moles per liter. But that's not the only... Oh, sorry, my handwriting's bad. I can see she's... If I need to write bigger, just go, write bigger. I'll do that. Right, but concentrate, that's an M for molarity. I didn't want to write all of molarity there. And this is a graph of blue food color dye reacting with bleach. So I have dye plus bleach, right? And as this reaction takes place, it goes from being, this is blue food color. It goes from blue to colorless. You're going to do an experiment like this. I'm actually in the process of rewriting because we tried it last semester and it was like way too complicated. So we're going to simplify it a little bit. But what you'll notice on this axis, this is the time. Remember we talked about when you want to measure a rate, you need some unit of time. So there's the time unit that's down here. And then you need to measure some quantity, one of the M's, like molarity, mass, that kind of stuff. And well, this is molarity times 10 to the 6, so it's actually, this is like 1 times 10 to the minus 6, actually. That's what that means. That's when they say times 10 to the 6. They, rather than write all the exponents over and over again, that's what they do. What's happening to the concentration as time goes by? Decreasing. It's going down. That's the colorless part. Right. When you take blue food coloring, it starts out blue, and when you put bleach in it, it goes from dark blue to light blue to colorless. And you see that transition. I had a video of it, but the videos aren't working, so I'm not going to try running it. All right. Now, rate When we say rate, it's just the slope. And when we say rate, we're just measuring a slope. So you'll notice that the average rate, okay, is the change in dye concentration over the change in time. Now, if I gave you a graph like this and calculate the slope and didn't tell you anything else about it, you could do it, right? You take rise over run. So you would take this value. Oh, actually, you know, I can do this. I always forget I can do this. All right. So you could take this value, this y value, subtract this y value, takes this x value and subtract that x value, and do rise over run and calculate a slope. You guys familiar with that? Mm-hmm. I mean, it sounds like something you've done before at least. That's what we're going to be doing in some of our experiments, is doing rise over run. Okay. The other way to do it, and then we'll look at some data and try this, but the other way to do it is do what's called an instantaneous rate. So back up for a second. Let me go back to that previous slide. Okay. This is what we call the average rate. The rise over run. And it's probably what you guys are most familiar with doing, is just making the rise over the run. Right? x2 minus x1, y2 minus y1, and the y's over the x's, and you're done. Okay? All right. This is the one you're probably not familiar with, but you have to get familiar with doing it. Okay? Now, I'm going to little side note. You don't have to have had calculus, but who's had calculus? Okay. Instantaneous. It's the instantaneous. So in order to do, we talk about the instantaneous rate. It's just the slope. Like if you take a point on a curve and you draw a line through it so that it is parallel to the slope at the point. I said words. They may not have made sense. You could say that didn't make sense. Did that not make sense? Does it make sense? Take a point, right? Draw a line through it so that the slope of this line is the same as the slope through this point. And then what you do is you do the rise over run off of the line. Oops. Keep doing that. Take the rise and the run like that. Now, honestly, you know what the easiest way to do this is? So this will be my rise. This is the change in y, and this is the change in x. And then slope is delta y over delta x. That's a y. The easiest way to actually do this is when you're drawing a line, just draw it all the way out to here. And if it starts at 0, 0, it's the y value divided by the x value. Because you subtract 0, because the origin of the graph is right here. So the rise for that is about 2.5. And the run is what? Oh, well, to here, actually, you go all the way, it's 5.5, right? So then you can just take one divided by the other, and that's the slope of that line. Okay. But that's known as the instantaneous rate, because it's the rate right at that point. It's the slope through the point rather than the slope between 2 points. Okay? That's the only reason. It turns out this is more accurate, but it's a lot harder to do because, you know why it's harder to do? Because you have to draw the line. Right? And then the way people draw lines, everybody gets a little bit of a different line. Now, there's a homework problem. You have to do it, and it's going to be a little bit frustrating. There's a homework problem where you have to do the instantaneous slope, and you're going to get mad at me when you do it, but it's there. Just do your best. It's one question out of a billion. So for the semester. I try to assign not as much homework as like some people do. Okay. So we were going to write stuff that looks like this. So let's say I have a reaction. It's A goes to B. Okay? Simple reaction. Stoichiometry is 1 and 1. If A goes down by 1 molarity unit, what does B go up by? Look at the stoichiometry. It's 1 and 1, right? So A goes down by 1, B's got to go up by 1. Because it's a 1-to-1 stoichiometry. If I use up 1 mole of A, I'll produce 1 mole of B. Because the stoichiometry is 1-to-1. So the rate of the reaction, and we're going to call this the reaction rate. I'm going to complicate it here in a little bit. I apologize, but the reaction rate RR, we're going to do that over and over again, RR, is related to the concentration changes. So this is supposed to be reaction rate, not just rate. I kind of screwed that up. So put another R there. Now I'm going to go back 1 slide so you can see it. Actually, I'm going to go back several animations. This slope, this is for the concentration of reactant like A. What's the concentration doing? We said it already.
Decreasing.
It's decreasing, right? Which makes sense because in a reaction, as the reaction goes forward, the concentration of the reactant should go down, right? Because you're using it up. What's the product doing?
It's increasing.
It's got to be increasing because it's the product, right? You're making it, right? So you have 2 different graphs that you have to start to think about. You have this graph for the reactant as it goes down, but you also have a graph for the product as it goes up. The rate at which those graphs go up and down depends on the stoichiometry, right? It's going to depend on how much of each is used or how much of each is produced as the reaction goes along. So that gets us back to this point. Sorry. Gets us back to this point where I have a negative sign here, right? Now, I have a negative sign there. Sorry, go back to that. I have a negative sign there because I want the reaction rate to be a positive number. That's the only reason the negative sign's there. For the product, since it's going up, if I calculate the slope change from the product, it's going to be a positive number. But for the reactant, it's always going to be negative, and so because we don't like negative numbers, we put a negative sign here. So that's the slope for the reactant is going to be negative. If I put a negative down here, on this side, it'll be a positive number. That's the only reason for that, okay? So you guys kind of get the idea how a reaction rate is measured, right? Okay, so one thing I want to make clear, though, is the rate and the reaction rate are different. All right, the rate can be negative, but the reaction rate's always got to be a positive number. The rate is just the slope, but the reaction rate, we want it to be a positive number. So that's why we put the negative sign in there, so it would be a positive number. Okay. So then I made a little note here. Right? Reaction rates also have to incorporate stoichiometry, so I'm going to show you how to do that so that the reaction rates that you calculate for reactants and products give you the same number. Okay? But I also wrote these things. Right? The reaction rate is actually how fast, this is the reaction arrow, is going. It's not how fast the concentrations are changing, they're related, but it's how fast the reaction is actually going. And then rate is how fast the concentration is changing. By the way, the brackets mean concentration if you didn't catch it on the previous slide. The brackets mean concentration. And then the rate constant, which we'll get to in a little bit, right, is used to relate concentration changes to reaction rates. So just keep those things in mind. You don't have to totally understand that part right now. But the idea was you can always go back to that slide and say, well, what are the things that aren't the same? It's just right here. Go to this slide. And trust me, when you get to test time, you'll be like confused. You'll be like, what? Which one of those is not the same as the other? Because it's rate, reaction rate, and rate constant. And they all start to sound the same after a while. So try to keep those straight in your mind. So here's a reaction. It's 3A goes to 2C. I use letters all the time. So when I have reactions and I have these complicated molecules, right, I just replace them with letters. Right? Because I want the stoichiometry. That's what I care about. But I don't want to have to write like N2O4 over and over and over again. I don't want to write PO43 minus bracket 2 over and over and over again. So that's what I do that. Okay. Oh, sorry. Go back to this. So I have this reaction that looks like this. So how am I going to relate? So if I have the change in concentration of A, so I'm going to do some notes on here. There's nothing written on this slide. Concentration change for A divided by the concentration, the change in time. I want to relate that to this. Okay. First of all, we know that the sign for A is negative, right? So I got to take care of that. So in order to take care of that, I'm going to go like this. Because I want to relate these two things together. Now, if three A's react, I get how many C's? I get 2, right? So those aren't exactly the same, right? And so what I want to do, if I want to relate this side to that side, I have to use the stoichiometric coefficients to take care of that. Okay? The simple way to do it is just to do it like this. And those two calculations give you the same number. Because for every 3 A's that go, right, I'll divide by 3. And for every 2 A's that are produced, I'll divide by 2, and that reduces it down to 1 and 1. So this is how we take into account, this is how we take into account the stoichiometry of reaction. Those will give us the same numbers regardless of whether we're measuring the reactants or the products. So we can measure reactants changes or products changes, and we still get the same number. This is the reaction rate. When I say RR for this reaction is minus 1/3 times the change in A over the change in T. Okay, so I just did something here. I got rid of the brackets because I'm already tired of drawing brackets. It's okay if you leave the brackets off. Better draw my A's a little better. I see critical eyes. Is equal to 1/2 times the change in C over the change in T. All of those are equal to the reaction rate. And that's how we make it the same number. So now, in essence, I've converted, remember I said the reaction rate is how fast the arrow is going, right? How fast the reaction arrow is going. This helps me convert it into how fast the reaction arrow is going, that 1/3. The other way you can do it is just use stoichiometry, right? If you know the reaction rate for A, right, you multiply it by 2/3, the stoichiometric coefficients, and you'll have the rate of change for C. I mean, you can do conversions like that, but you can use stoichiometry to convert one side to the other as well. All right. In general, oh wait, how long do I go? We started at 12, so I go to 1:15 now. Okay, good. Oh, yeah, and then you guys have been so good, I'll give you Monday off. Now, actually, Monday, isn't that the holiday, Martin Luther King Day? It's always like the second Monday of the spring, just so you know. Oh, and who walked in late? You walked in late? Are you adding? You're in the class? Okay. Just come up to me afterwards so I mark you so I don't drop you later. Oh, and everybody has lecture notes. And I haven't handed the syllabus out yet. I just started with lecture. There. Oh, and I don't care which lecture you guys come to, by the way. I do care which lab you come to. Like, you guys can always go to the other lab. The other lab can't always go into your lab. Because there's like only 12 people in the other lab. And if you want to feel like you have your own bench, right? Feel free to go to the other lab. Huh? It's, okay, so that class starts at 12:30. So it's a half hour later than this lab, but it's on Tuesdays, Thursdays.
Same room.
Same room, yeah. So I don't care, but you're going to be enrolled in this class still. You just can come to the other lab if you really need to. So like if you have a work schedule conflict or got to take your mom somewhere, or that's what I end up doing a lot, take my mom somewhere. Like you got to go to something like that, just let me know and we'll just make arrangements for you to be there on a different day.
Do we have lab today?
We're checking in, yeah. Do you want to check in tomorrow? I'm okay with that too, but you got to come. And we're going to go over the syllabus, and we're going to do like that important stuff. But if you want to get a locker, you got to show up today to get your locker for your class. Just what it is. Okay, so reaction rate and stoichiometry. Get on task here. Reaction rate and stoichiometry. This is how we do it. Okay, so if you have a reaction, these are the This is the Oh yeah, sorry. No. It's working really well though. And it's all recording still. Usually, like, craps out on me. So I have a YouTube channel. If you want a good YouTube channel, go to my wife's YouTube channel. I don't lecture to the book. She goes through the book section by section and does like lots of examples. I'm the conceptual guy in the family, and then she just bosses me around. It's okay. It's worth it. Okay, so this is a coefficient. And this is the reactant, right? So you notice how for all the reactants, I have a negative sign. And then I divide by their stoichiometric coefficients, and that gives me reaction rate. You can also calculate the reaction rate from the products by dividing by the stoichiometric coefficient, but you don't need the minus sign because the products are naturally going up in concentration. I like Dexter. So I have lots of Dexter things. Does that make sense? Yeah? Not the fact that I like Dexter. I mean, does it make sense? That's what's on the slide. Okay, so let's try this. We're going to calculate the average initial rate. And I actually did one for you, but you can follow through with me. Now, normally we want these things to be in molarity units. And you'll notice that this is time on, there's the time here, okay? And this is concentrations of the reactant or concentration of the product, right? And I'm going to calculate the reaction rate. And this is 1 millimolar. And so I converted to molar. I need to convert to molarity units. So what's a milli? You'll see it all the time in this class. 10 to the minus 3, yeah? 10 to the centis 10 to the minus 2, millis 10 to the minus 3. You got to remember that, right? And so what I'm going to do is I'm going to calculate a slope. Now it says initial rate. Which points do you use for the initial rate? The first two, because it's the very beginning, right? So we're going to do the initial rate. And if I wanted to calculate rise over run, those are the points that I would use. To give me average rate. So I'm going to get an average rate off of this, right? It's 0.74, that's Y2, minus 1.0, that's Y1. That's the change in Y. And the change in X is 10 seconds, it's 10 minus 0. Doesn't matter which order you do that in as long as you're consistent. right? They're either both going to be positive or both going to be negative in this case. That actually gives me a negative number. The coefficient, though, is 1, and I put a negative sign in here. I get 2.6 times 10 to the minus 5th molarity units per second. So that is the rate of the chemical reaction. Now, remember what we were doing is I gave you both sets of data because we want to also make sure that the reaction rate calculated from the product ends up being the same thing. And so you'll notice there's a 0.26. I'm using this data here. Times 10 to the minus third and 0 times 10 to the minus third because it started at 0. Okay. That's going to give me 2.6 times 10 to the minus 4. The change in time is the same because it's the same time interval, so it's 10 seconds again. And I end up getting this. I get the same answer for both because that's the reaction rate. They're both from the same reaction. You should get the same reaction rate. If you don't, if you get this on a test and you don't get the same answer, you forgot something, right? This is going to seem, by the way, a lot more like a math class in the first chapter than a chemistry class. We're just starting. There's just going to be more and more. Okay. Just to show you something else, you can calculate reaction rates for anywhere, right? And you'll notice, like I did the initial reaction rate, that's up on the top. 2.6 times 10 to the minus 5th, and I also did the reaction rate down here, and it's 6.0 times 10 to the minus 6. Which one's faster? Which one's slower? The first one, right? First one's faster. And you can tell that because remember, reaction rate, all it is the slope. It's related to slope. So if you look at this, right, you can see automatically this slope is higher than this slope. This one's closer to being flat, right? And so you can see the reaction rate is going down. Now, let me ask you a question. Why is the reaction rate going down? Concentration. Because concentration is going down. Remember? Reaction rates, one of the things that influences reaction rate is concentration. In this particular instance, you're seeing the concentration go down, so the reaction rate goes down. It's not true of every reaction type, but in this case, it's true, okay? Okay, a little bit different. I just wanted to show you how this works. Another reaction, right? This time I'm just doing for B, and the stoichiometry is A goes to 2B. And here are the concentrations right here. So if I want to calculate the rate of change, initial rate change for B, right? I'm going to do rise over run. So this is the 0.52 from here. Right? And this is the 0 from here. Sorry, made a mess out of it. So the rate at which B is changing, this is rate, is that. Right? But the reaction rate, you have to take into account the stoichiometric coefficient. And so I'm dividing it by 2, and so it turns out the reaction rate for this reaction is this. Okay. Now I set this up so it'd be exactly the same as the last one. I actually just made the data do that. Okay. But we take into account stoichiometric coefficients to get reaction rates. This is just the rate of the reaction, or the rate of the change of the concentration. All right. See why I gave you the slides, by the way? There's like no way to keep up with this if you don't have the slides. If I can get away with it, I'll bring you the set for the next time too. But this is like 2 weeks worth of slides. Okay. And if you have trouble printing it at any time, just let me know and I'll have copies printed for you guys. I don't think the production people here want me to print all the slides for all the students all the time. But if you can't do it, let me know and I'll do it for you. Okay. These ones, I went to City College last night. I used to work there. Middle of the night, printed like 500 copies of stuff. I just took my wife's keys. That's where she works. Yeah. And then I came home and said, you know, your printer's low on toner. Okay. Another example of what we can do with this information, okay? I don't even know where I am anymore. I know I'm here. I just don't know where in my slides I am. Okay. Although it's not too long, probably 10 years from now, I won't know I'm here either. So relating reactant and product changes to reaction rate. So it says for the reaction, 2A goes to 2B. The reaction rate is 1.5 times 10 to the minus 2 molarity units per second. What are the rates of the change in A over time and the change in B over time? Okay. So I want to know, what are the concentration changes for these two? So this is reaction rate. So I have one, oops, sorry. Gotta go back. Oh, that's right, I just recorded that. I'm in trouble. So the reaction rate, right, is equal to negative 1 over 2. Now, this is for 2A, right, times the change in A over the change in time. Now, your book is not, when they give you problems like this, they often don't say, hey, what's this? They just say, what's the concentration changing rate? Right? So I wrote it there to help you see how you do this. Well, how do you do that? Well, you just solve it like this. And a lot of people get like freaked out, like, but what's that? That's what you're solving for, right? It looks like it's got unknowns in it, but it says what's the reaction rate. That's actually what you're solving for. So then it becomes minus 2 times 1.5 times 10 to the minus 2 molarity units per second. So that becomes negative 3.0 times 10 to the minus 2 molarity units per second. Well, that's the answer for that. Okay. So that's how you do it for A. You do exact same process for B. Okay. So for delta B, oh, sorry, let me do this. The reaction rate is equal to 1 over 2 times the change in B over the change in T, like that. And what do you end up with? Well, you'll solve it. So that's 3.0 times 10 to the minus 2 molarity units per second. Sorry, I got a little messy. So what's the difference? The sign's the difference, right? Product's going up. That's what it's telling me, and the reactant's going down. The number's exactly the same because it's 2 to... I shouldn't have made it 2 to 2. I should have made it something else, because 2 to 2 should be 1 to 1, right? But anyways. Yeah. But the signs are different. All right, let's do another one. Oh, wait. Sorry, were you done writing?
Oh,
Yeah.
You want us to show work when we know it's just positive?
Yes. Yeah, the answer is yes. Because most likely it'll be like 2 and 3 or 5 and 6, or, you know, it won't be the same. So you get a different number. Show the work, the rearrangement, plug the numbers in. I like that kind of thing. It makes me happy. Okay, so we're going to talk about rate laws. Okay, so what is a rate law? That's maybe the first thing I should talk about. Well, did I write it on here? Maybe I didn't write it on there. I didn't mean to do animations on all of this. Wait, I thought I had a little slide that said this is what a rate law is. Doesn't it have a slide that says this is what a rate law is? Mm-hmm. I do. I skipped a slide somehow, huh? Oh, yeah, there it is. Oh, that's how I did it. Okay, rate law. So this is definition. Rate law is a mathematical relationship between the concentration of reactants and the rate of a reaction. So far we've been like measuring rates of reaction, right? But what's the relationship between the concentration and the reaction rate? That's what we're looking at. Right? And when you write a rate law, it's going to look like this. Generically look like reaction rate, okay, is going to be equal to K times the concentration of the reactant, but it's going to be raised to some power. I'll just make it X. Doesn't really matter what symbol you use up there. Times the concentration of a product, the other reactant. I'll just call it Y. A lot of times they use M and N because I get tired of seeing X and Y all the time. But whatever you want to stick up there is fine. So that's what a rate law looks like. It's the reaction rate. This is known as the rate constant. And it's what makes that into an equal sign. These X and Y see, that's why I hate doing X and Y, because now it looks like I'm doing like a coordinate. Sorry. The exponents are known as the orders. The most common orders, there's 3 common orders that we see, but they don't have to be, but there's 0, 1, and 2. Those are the most common orders. So like X, like the X on A could be 0, 1, or 2. Now if it's 0, then what's the number raised to the 0 power? It's 1, right? It's always 1. So, and then if it's 2, then 1, it's just whatever the number is, right? If it's 2, it's squared. You have to square the number. So this is the way these things look. Now they can be half orders, like X could be 0.5, it could be 0.6, it could be other numbers, okay? But actually those orders are telling us something really important. They're telling us how the reaction actually takes place. Like how many molecules have to collide in order for this reaction to take place? All right, remember I said 2 molecules have to collide in order for reaction to take place, have the right orientation? Sometimes 3 molecules have to collide. It's pretty rare, okay? So we'll get into that. Some important ideas about rate laws, and then we'll be done for today. As far as lecture goes, we'll take a break and then we'll head over to 80, whatever it is, too. Okay. Some important ideas about rate laws. We always have to figure it out from data. It's not based on the stoichiometric coefficients. Okay. Always based on data. How do you, it just give you a quick idea how it's done. You change the concentration, you see how the rate changes. And that tells you what the order for that is. It tells you what the X and the Y's are, or what the M's and the N's, as you'll see as I use later. Okay. In order to do that, right, you have to measure the rates of each, you have to measure the rates with the reaction. There's a, I didn't mean to write that there. Hang on, let me fix it. You have to measure the rates with each reactant at different starting concentrations. So you got to do the experiment a minimum. Like if there's just one reactant, you guys a minimum you got to do the reaction twice, 2 different concentrations to see how it changes. Okay. And we usually use the initial rate to do this. Okay. The reason we use initial rate is it's not usually complicated by products being in the solution, because the concentration of the products are usually very low at the initial part of the reaction. Yeah, and then we do comparisons of rate changes versus concentration changes, and that tells us what the form of the rate law is. It tells us that what the values for X and Y are. All right. Oh, we have 5 minutes. I'll just show you this one. I'll do it again at the beginning of the next lecture. Remind me to start here, okay? Let's say I have an experiment, right? It's A plus 2B goes to 3C. And in the experiment, you'll notice there's 3 of them. In the first 2 experiments, what happens to the concentration of A? It's the same. What happens to the concentration of B? It doubles, right? But what happens to the rate? It stays the same. Right? So what that's actually telling me, right, is that B doesn't matter. The order for B is 0. Does that make sense? I'm going to talk you through it. We're going to actually go through it like step by step. But if B's changing and the initial rate isn't changing, then the concentration of B doesn't matter. So I know in my rate law, there is no B in my rate law. Now, the next experiments that we'll look at, right, we'll look at experiments 1 and 3. Now, why do I look at experiments 1 and 3? Because I get a change in A, but I don't have a change in B. And one of the sort of standard rules in science is change one variable at a time. Otherwise, you can't tell what caused the change in the outcome. Okay? So we change one variable at a time. And so I keep this one the same. You notice what happened here. I kept this one the same, and I changed this, and it was very easy to tell that B doesn't matter. Now what I do is I take this, and I go from here to here. B doesn't change, but A is doubled. And what happens to the rate? Quadrupled, right? 16, right, is 4 squared. Isn't it 4 squared? Oh, 4 times 4. Yeah, it's 4 times 4. Yeah, it's 4 squared. It's second order. All right, I just went through that for fun. It's a second order. So I actually know just by looking at it that this is 0 and this, is 2. And so I know the rate law. That's how you do it. You look at how the concentration changes, and you look at how the rate changes, and you figure out what the orders are. And that's how you figure out the rate law. So I'll take you guys through this problem again at the very beginning of the next lecture. I've got lots of slides on it. We'll break it down, okay? But I wanted you to see the big picture. All right. Good. Meet over in 82 in 10 or so